Greenhouse gases differ not only in the wavelengths of electromagnetic radiation that they absorb and the degree to which they absorb a particular wavelength, but in their concentrations and chemistry in Earth's atmosphere. All greenhouse gases participate in chemical reactions that limit their residence time in the atmosphere. For example, carbon dioxide dissolves in water and forms carbonic acid. We can compare the warming potential of greenhouse gases relative to carbon dioxide based on their mean residence time and absorption characteristics. The total radiative effect of a greenhouse gas thus depends on its concentration and warming potential. In summary, greenhouse gases do not influence the amount of electromagnetic radiation that Earth emits to outer space. Rather, they alter the temperature of the surface and the wavelengths that escape. Higher concentrations of greenhouse gases warm the surface and shift outgoing radiation to wavelengths at which the greenhouse gases are transparent. For example, higher concentrations of carbon dioxide in the atmosphere would increase the depth of the notch at 15 micrometers, but this would be compensated by a warmer planet that would emit more radiation at shorter wavelengths. Clouds exhibit schizophrenic tendencies with respect to Earth's energy budget. They reflect incoming solar radiation and thereby promote global cooling. Simultaneously, they absorb long-wave radiation from Earth's surface and radiate some of it back to the surface, thereby promoting global warming. On balance, however, clouds reflect more solar energy than they emit back to the surface. Clouds generally cool Earth more than they warm it. Ocean waters circulate around the globe and establish patterns or currents that derive from A. differences in solar energy received by the equator or the poles, B. topography of the ocean floor and coastal land masses, C. rotation of the Earth around its axis, and D. changes in seawater density. Seawater becomes denser as it cools or as its salinity increases from the removal of fresh water during evaporation or ice formation. Conversely, the density of seawater diminishes as it warms or as its salinity decreases with the influx of fresh water from rivers or melting of ice. One major pattern of ocean currents, the so-called global conveyor belt, or thermohaline circulation, involves the northward flow of warm surface waters from the Caribbean along the Atlantic coast of the United States, the Gulf Stream, continuing along the Atlantic Ocean toward Great Britain, the North Atlantic Drift. These warm currents raise the average temperature of the east coast of the United States, west coasts of Europe, and Scandinavia above 5 degrees Celsius above other landmasses at the same latitudes. In the North Sea, these waters become denser as their temperatures drop and as they become more saline from evaporation of surface water and ice formation. The denser waters flow south, the Greenland and Labrador currents, and sink to between 1,200 and 5,000 meters in depth. Eventually, they reach the Antarctica and veer eastward. This deep, cold current, the Antarctic Circumpolar Current, spills both around the Horn of Africa and around New Zealand, and heads northward. Passing across the equator, these waters warm, rise to the surface, and join the general westward flow, the equatorial currents, across the Pacific, Indian, and finally Atlantic Oceans.